Everyone, I hope you are doing well. In this video, I'm gonna talk about match filter. I'm sure you heard about match filter, and because in many scenarios, in many applications, we can see match filter, especially in digital communication systems, in wireless communications, and in radar and sonar systems. In a communication system, we need to maximize signal to noise ratio at the receiver. For that, we have to design a filter optimally, which we call it a match filter. Let's consider a deterministic signal. It's not a random process, it's not a stochastic process, it's a deterministic and known signal. And it's corrupted by additive white noise, which is a white centrostationary process, and the power spectral density is constant, equals to eta over 2. This is the noise power spectrum. And we have received signal, for example, x of t equals to s plus n. At the receiver, we filter the signal. Signal is a LTI system, and the impulse response is h. And I'm looking for optimum filter to put here. After filtering, we sample the output, and for example, in time instant of t0, we get voltage. Let's consider the output voltage yt, and here we have one sample of yt0. Okay, I'm gonna do some math and try to form signal to noise ratio and then maximize it. But we know the input-output relation of LTA system is convolution, and we have yt equals to xt convolution with ht. There will be two terms at the output, one from signal and others from noise. Terms related to the signal, I call it SOT equals to minus SOF I use inverse Fourier transform to show SOT. SOF in frequency domain is input signal spectrum multiplied by frequency response of the filter, and we have this. Then we want the signal at time instant of t0. So we have and the power for this voltage, it's power of 2, so the power of signal S equals to this term, which is Okay. And the power of noise. Noise is a stationary process, so the time instant doesn't impact on the power because the power for a WSS process is constant. So I can write this. It's the area under the power spectrum. And the power spectrum is the power spectrum of the input, eta دوم, multiplied by magnitude square of the frequency response of the filter. Now I can form signal to noise ratio. And I want to maximize signal to noise ratio with respect to H. I'm gonna find impulse response or frequency response to maximize this term. For this, I have to use Cauchy-Schwarz inequality. Cauchy-Schwarz say so. If you see these terms, they are similar to this term. I can, for example, I can define F as HF, for example, and we reach to the equality when one signal is multiply of the other signal. For example, Fx or equals to G conjugate of x. Based on this, I can write so for reaching to the maximum, F, which is should be a constant, S conjugate E minus the PF T7. If we take inverse Fourier transform, we can see the impulse response equals to K S T7 minus T. We call this match filter. And the signal to noise maximum signal to noise ratio is this term. I can write it here. Based on Parseval relation, this is the energy of signal and this is the noise spectrum level. And this term is the maximum signal to noise ratio. Duration T and amplitude 1. And match filter is as conjugate doesn't impact because it's a real signal, as t surf minus t, and s minus t is time reverse of our pulse, and we can shift the signal, and I can shift it with, for example, t to find the match filter. It means I put t surf equals to t. So this is the signal and this is the filter. If we convolve these two, we have this, and this is the time instant t when both signal overlap completely, and we can see the convolution will be equals to t. And the voltage that we get in time instant t will be t